All right, let's take a look at this study guide. So for each of these problems, I have already filled in our 5 variables. So we're going to approach each problem, try to assign our variables to numbers from the problem, pick out an equation, and solve for the answer. So number 1, airplane accelerates down a runway at 3.2 meters per second squared. This unit automatically tells me that's my acceleration. It also says in the problem that's an acceleration, but the meters per second squared is the indicator that is an acceleration. So I'm going to put it under A. For 32.8 seconds. Seconds is time until it finally lifts off the ground. Determine the distance traveled before takeoff. So determine the distance traveled, well, that's not going to be a velocity. That's going to come from displacement. And now my extra piece of information comes from just realizing what the situation is. An airplane is accelerating down a runway. Well, when an airplane takes off, it takes off from what velocity? It has to start at 0. It's going to speed up down the runway and then lift off the ground. So my initial velocity should be 0. If that's the case, I'm looking at using the second equation. My displacement is the unknown. Initial velocity is 0. Acceleration is 3.2. Time is 32.8. And that time is squared. So 0 times anything is 0. So that middle term goes away. Then 1/2 times 3.2 times 32.8 squared is 1,721 meters. There are some decimals after that. I'm just rounding up to that displacement. All right, number 2. A race car accelerates uniformly from 18.5 meters per second to 46.1 meters per second. I see meters per second on these. Those are velocities. It says going from 18.5 to 46.1. So the 18.5 is my initial. 46.1 is my final. It took that 2.47 seconds for that to happen. That is a time. Determine the acceleration of the car and the distance traveled. Well, I'm looking for both of these now. Since it says determine the acceleration, let's do that first. If I'm determining the acceleration, that means I'm going to ignore this displacement and focus on the variables that I do have. If I'm doing that, I'm going to use the first equation. (46.1) equals 18.5 plus A times 2.47. A times 2.47. I'm going to subtract 18.5 to the other side. You get 27.6. Divide that by 2.47, and you get an acceleration of 11.2 meters per second squared. So that's my acceleration. How do I solve for? It's 11. Put this here real quick. 11.2 meters per second squared. Now I want to solve for displacement. I could literally use any of my equations because I have 4, not 3 variables. Let's just use the third one. So final velocity, 46.1. I need to square that. Initial is 18.5. I need to square that too. Acceleration is 11.2. I'm looking for displacement. So 46.1 squared, 2,125.21, 18.5 squared, 342.25. 2 times 11.2 is 22.4. So if I subtract 342.25 from both sides, and you get 1782.96 divided by 22.4 And the displacement is 79.6 meters. Now we have a feather dropped on the moon from a height of 1.4 meters. The fact that that's meters tells me that my displacement is a negative 1.4. Why is it negative? Because the feather is dropped, and so it is moving down. The acceleration of gravity on the moon is 1.67 meters per second squared. Again, that is negative because acceleration of gravity points down towards the surface. Determine the time for the feather to fall to the surface of the moon. So I'm looking for time. So I must know one more piece of information. Anytime you see something that is dropped, anything that is dropped and is moving through the air, to drop it, you have to let it go from 0 meters per second. You're dropping it from rest. If you hold something and you drop it, it's not moving. When you drop it, it begins to move. So if I've got these as my variables, I don't see anything written beside final velocity, I'm going to use the second equation. My displacement is negative 1.4. Initial velocity is 0. Acceleration is negative 1.67. And I don't know time. So you may immediately think, well, I've got two different times here, one squared, one's not. This is going to be an issue. It would be if the initial velocity wasn't 0. This 0 times that t, anything times 0 ends up being 0, so it doesn't matter what t is. That middle term multiplies out to be 0. So if I write it again, negative 1.4, a half times negative 1.67 is negative 0.835. I'm going to get t squared by itself by dividing by negative 0.0835. I'm going to get 1.68, but that's t squared. To get t, I need to take the square root of both sides to undo that squared. So if I do that, I get a time of about 1.29 seconds. All right, number 4. Bullet leaves a rifle with a muzzle velocity of 521 meters per second. While accelerating through the barrel of the rifle, the bullet moves a distance of 0.840 meters. Determine the acceleration of the bullet. Okay. Now, why did I just skip the 521 meters per second? Because it's a little difficult at first glance to figure out, is the 521 the initial or the final velocity? Well, the context of the problem kind of helps me here. While accelerating through the barrel of the rifle. So my problem here is from when the trigger is pulled to when it leaves the barrel. So when the trigger is pulled, what's the velocity of the bullet? It has to start at 0. When it leaves the rifle, that's what muzzle velocity is. When it leaves the rifle, it leaves that barrel, the final velocity would be 521 meters per second. So I don't have anything written beside time. I'm restricted to the third equation. Final velocity is 521, that's squared, equals 0 squared plus 2 times a, I don't know that, times 0.84. So 521 squared is 271,441 equals, I'll go ahead and multiply the 2 and the 0.84. I get 1.68 times a. So my answer would be when I divide both sides by 1.68. And you get 161,572 meters per second squared. Moving right along, if you noticed, I've blurred out or boxed over number 6. Number 6 actually doesn't really apply to our situation. It's not a uniform accelerated motion problem, so we're going to skip it and ignore it. But number 5, an engineer is designing a runway for an airport. So again, a plane is taking off. Several planes use the runway, and the engineer must design it so that it is long enough for the largest planes to become airborne before the runway ends. If the largest plane accelerates at 3.3 meters per second squared and has a takeoff speed of 88 meters per second, so if it's taking off at that speed, that would be the final velocity at the end of the runway. That means the initial would be 0. Then what is the minimum allowed length for the runway? So what's that question asking for? Is it a displacement or a time? That is definitely a displacement. So looking at those variables, I don't know time. I didn't write anything beside it, so I'm restricted to the third equation. So my final velocity needs to be 88 squared equals 0 squared plus 2 times 3.3 times my displacement. So 88 squared is 7,744. 2 times 3.3 is 6.6. So displacement is going to come from dividing both sides of the equation by 6.6. And you get 1,173.3 meters. So that would be the length of the runway. Let's go down to number 7. Run Out of Gas is driving through town at 25 meters per second and begins to accelerate at a constant rate of -1 meters per second squared. Eventually, Renata comes to a complete stop. Represent Renata's accelerated motion by sketching a velocity time graph. Use kinematic equations to calculate the distance which Renata travels while decelerating. Then use the velocity time graph to determine this distance. Okay, let's do the kinematic equation stuff first and then talk about how it relates to graphs. So she's driving through town at 25 meters per second and then begins to accelerate. So the 25 is actually our initial velocity. Our acceleration is a -1 meters per second squared. And it says eventually Renata comes to a complete stop. So that means at the very end, what's our velocity? Our final velocity is 0. So we want to know the distance that she travels while decelerating. So for an equation, I'm going to look for displacement. Again, I need to use the third equation. So my final velocity is 0. Initial, 25, that needs to be squared, plus 2 times -1 times the displacement. So 25 squared is 625. And then this becomes -2 because the -1. So if I add this term to both sides, you get 2 times delta x equals 625. And so delta x would be 625 divided by 2, which is 312.5 meters. So that's how far she traveled while decelerating. How would I get this using a graph? Well, velocity time graph. Let's do this again. So velocity, let's leave room for numbers. Her velocity starts out at 25 meters per second. So this begs into question, what does our acceleration mean? What does it mean to have an acceleration of -1? That means every second I'm adding -1 to 25 meters per second. So at 0 seconds, her speed is 25. At 1 second, I'm adding -1, her speed becomes 24. Another second later, take away 1 again, or add -1 again, I get 23. I can keep going so on and so on, each second adding -1, and we see what's happening to my velocity. My velocity is going down because I'm adding -1, and my velocity is positive. Well, let's think about this. When would my graph reach 0? When would my velocity reach 0? Well, if I keep going on this pattern and I keep subtracting 1 each time, it'll reach 0 after 25 seconds. So my velocity graph looks like this. So going back to reviewing what we already know about velocity graphs, This is moving in a positive direction because it is above the x-axis. Since the graph is going towards 0, it's slowing down, and I know this makes sense because the problem tells me she comes to a complete stop. And so how would I get the distance traveled from this graph? Remember, to get displacement from a velocity graph, I have to take the area. So let's take the area of this graph. So remember, how do we take the area of a velocity graph? This one is a triangle, so I need to do 1/2 base times height, which would be 1/2 of 25 times 25, which again gives me 312.5 meters. So just presenting two alternate ways to get the exact same solution. One using the kinematic equations, one using graphs. So that kind of tells us that using these graphs is kind of how we came up with these equations in the first place. So now let's move on to number 8. Otto Emissions is driving his car at 25 meters per second. Otto accelerates at 2 meters per second squared for 5 seconds. Otto then maintains a constant velocity for 10 more seconds. Determine the distance Otto traveled during the entire 15 seconds. So, this is one of the problems that has actually two parts to it. Otto is speeding up. So let's draw a picture here. Otto starts at 25 meters per second. Then he speeds up for 5 seconds. And then after that, he maintains a constant velocity for 10 seconds. So this is 5 seconds. The acceleration is 2 meters per second squared. Constant velocity means my acceleration is 0 meters per second squared. So we're trying to figure out the entire distance for the entire 15 seconds. Excuse me. So we can do this using our equations. So let's break it up section by section. The first section is this red section here. The time is 5 seconds for that section. The acceleration is 2 meters per second squared. The initial velocity, 25 meters per second. What we need to do here is, excuse me, figure out how far or how long this red section is. How far did he travel in those 5 seconds? So I'm looking for displacement. That looks like it's going to bring me to my second equation. So this displacement is 25 times 5 plus 1/2, 2 times 5 squared. And I'm just going to plug that straight in the calculator. And you get a distance of, let me draw correctly here. You get a displacement or distance of 150 meters. So this is 150 meters. Now I need to find the blue. So if I erase this, and now I try to fill this in with my blue information, well, change the color. In the second section, the time is 10 seconds. The A is 0 meters per second squared. We're looking for displacement. And so I need one more piece of information. I need to know what is the initial or final velocity. Well, if we think about it, if my acceleration is 0, this initial and final should be the same. An acceleration of 0 means my velocity was not changing. So I need to figure out, okay, what was my initial velocity here when this 10-second section started? Well, that initial velocity is the final velocity of the red section. Wherever the red section ends is where the blue one begins. So at the end of the 5 seconds, whatever speed you got to, you're going to continue at that velocity for 10 seconds. So what I'm going to have to do first is go back to the red section. And in doing so, I need to solve for that final velocity. So I'll fill in the information again. So the easiest equation to use right now to figure out that final velocity is probably our first equation, which is final velocity equals initial velocity plus acceleration times time. Final velocity is 25 plus 2 times 5. So the final velocity here, 35 meters per second, which is the initial velocity of the blue section. So, again, let's switch this to the blue. I'll just write it again over here. So, looking for displacement, initial velocity is 35 meters per second. Final velocity is also 35 meters per second because it's not changing. Acceleration is 0, and then time is 10 seconds. So anytime your acceleration is 0, you can just think of your constant velocity equation, or anytime your anytime your acceleration is 0, you can use the second equation. And we're going to do this in our later units as well, and we'll see why. If I plug in an acceleration of 0, then this whole last term goes away because I'm multiplying by 0. So I'm just going to get 0 for that term. So I'm just left with displacement equals initial velocity times time, which 35 times 10 would be 350 meters. So now the blue section was 350, the red section was 150. So the total displacement was 150 plus 350, or 500 meters. All right, so now let's go to number 9. This one also says consider using a velocity time graph. I did not in number 8, so I'm only going to solve number 9 by using a graph. It's the complete opposite of number 8. You start out with a constant velocity, and then your velocity changes. So I personally think these types of problems are easier if you know how to sketch a quick graph, and I'll show you why. That was a lot of work we did in number 8. We actually had to do 3 equations to solve those 2 parts of motion. But think about this. If Chuck Wagon travels with a constant velocity of 0.5 miles per minute for 10 minutes. So if this is 0.5, and this is miles per minute, then he travels at that constant velocity for 10 minutes. Chuck then decelerates at negative 0.25 miles per minute squared for 2 minutes. So what does that mean? It's not in meters per second squared, but I can think of it the same way. So if I decelerate at negative 0.2 miles per minute squared for 2 minutes, what that means is every single minute I'm adding negative 0.25 to my velocity. So that means 1 minute later, at 11, that velocity is now 0.25, because if I add negative 0.25 to 0.5, I get positive 0.25. If I go another minute to 12 minutes, I'm going to add another negative 0.25, and if I do that, I end up with 0. So our motion here is literally you're traveling at a constant velocity of 0.5 for 10 minutes. Then you decelerate at this rate for 2 minutes, so I'm going to subtract or add this negative for every single minute, and over 2 minutes that brings my velocity down to 0. So how do we get distance from this graph? Well, I take the area. So the area of this blue section would be, not blue section, the first constant velocity section would be 0.5 times 10, base times height, which would be 5 meters. Then this section is a triangle, So it'd be 1/2 the base times height. The base of this triangle is 2. The height is 0.5. So 1/2 times 2 times 0.5 would be 0.5 meters. So what's the total distance traveled? Well, I just add the areas together. 5.5 meters. See, if we know how to use a graph, it's a lot less work, and it actually might take less time to solve this problem. It works the same way for any of our other kinematic problems. You can use either approach you wish on the test. If you're not sure about the graphs, then stick with the equations. If you want to try using the graphs for some of them, be my guest and go ahead. All right, so the first 2 pages of the study guide were more about can I use the equations, our 4 kinematic equations, to solve problems. This, these second 2 pages are more about can I apply those equations to a specific situation of free fall. Now remember from our videos, free fall is when an object is not touching anything else and we're in a vacuum. So we're assuming every problem in this class we're in a vacuum. What that means is there is no air to slow us down. So nothing's moving through the air. I'm not having to push the air molecules out of the way. I don't have that resistance of air resistance, is what it's called. So now let's look at this problem with that lens. I already know what my acceleration should be for all these problems because I'm in free fall. Acceleration should be negative 9.8. He uses 9.81 in the videos. I'm just going to use 9.8 meters per second squared. So with that in mind, let's look at some of these problems. A rock is dropped from a rest position at the top of a cliff and free falls to the valley below. Assuming negligible air resistance, which means I can ignore it, use kinematic equations to determine the distance fallen and instantaneous speeds after each second. Indicate these values on the odometer and the speedometer views shown to the right of the cliff. So I'm looking at, this picture over here. Round all odometer readings to the nearest whole number. So it says show a sample calculation below. So the first second's already been done for us. If it looks like this paper is rounding, after 1 second, if my acceleration is negative 9.8, which can be rounded to 10 meters per second squared, that means every second we are going to add negative 10 to our velocity. So since I'm dropping this from rest, it's going to speed up in the negative direction. So after 1 second, the speed would be 10 meters per second, which I see here on the odometer. The speed is 10, but my velocity would be negative 10 because this object is moving downward. You can see that they got a distance or displacement of 5 meters, which means it has dropped 5 meters. How could I prove that? Well, let's look at our second equation. And honestly, if you ever just drop something from rest, you're probably going to use the second equation to solve for something, unless you're looking for final velocity. So the displacement in that first second, the reason why I want to use this equation if I drop something is because this first term becomes 0 because my initial velocity is 0. We'll go ahead and just use the rounded negative 10 it seems like they're using for my acceleration. And the time is 1 second. So if I multiply that out, 1/2 times negative 10 times 1 squared, I get negative 5 meters. So my displacement would be 5 meters there. So first, let's go through all these speedometers and figure out the speeds. Well, if after 1 second it was 10 meters per second, which I know is a negative 10 for velocity, what is going to be the speed after the next second? Well, the acceleration is still negative 10, so that means I'm going to add a negative 10 to that velocity, which makes it negative 20. So my speed would then be 20 after 2 seconds. Same thing for 3. Add negative 10 again, my velocity now is negative 30, so my speed is going to be 30. And do we see the pattern? It's just going to increase by 10 every single second, and it goes down to 5 seconds. So the speed increases by 10. I'm actually going to have to do some work to figure out the displacement. So the general form of the formula here for displacement is I'm going to ignore this first term because it's 0. So I'm really just looking at, excuse me, 1/2 AT squared. Because that initial velocity is 0, that term goes away. So I'm going to write those over here. For 2 seconds, that displacement is 1/2 times -10 times 2 squared. So that would be 1/2 times -10 times 2 squared, which would give us a displacement of -20 meters, which I know the negative just means down. So it just traveled 20 meters after 2 seconds. What about 3 seconds? 1/2 times -10 times 3 squared. That would be a displacement of -45 meters. So my odometer would read 45 meters. Keep going. 1/2 times -10. And again, I'm just using the rounded -10 because it looks like that's what they're doing here. Times 4 squared, which would be -80 meters. So my odometer would read 80. Why are these positive? Because an odometer in a car is just reading distance. It just adds. It doesn't really tell you a direction. So that's why I'm making these positive and not negative. But I know the negative on my answer means it is moving down. And then finally, 1/2 times -10 times 5 squared. Let me write that clearer. And that would be -125 meters. So 125 meters on the odometer. Okay, look at some of the questions again. At which of the listed times is the acceleration the greatest? Well, it's in free fall, and it's in free fall this entire time. Free fall is one acceleration, and it's -9.8. So none, the acceleration does not change in free fall. It is always at -9.8. Number 3 here, at which of the listed times is the speed the greatest? Well, I see my speedometer going up as I'm traveling down. The highest reading on the speedometer is at 5 seconds because as this falls down, it's progressively speeding up, and it's always going to do that. So the speedometer is greatest at 5 seconds. So that is where the speed is the greatest. If the falling time of a free-falling object is doubled, the distance fallen increases by a factor of what? Identify 2 times and use the distance fallen values to support your answer. So let's just look at 1 and 2. Between 1 and 2 seconds. So at 1 second, at 2 seconds. At 1 second, the distance fallen was 5 meters. At 2 seconds, it was 20 meters. So by what factor did the distance increase? And what I mean by that is, what do I multiply by 5 to get 20? So when the time doubled, the distance increased by a factor of 4. So it was actually 4 times the amount of distance. And why does that make sense? Because if I'm using my formula of 1/2 AT squared, when I double the time, that double, like times 2, that double is actually squared. So when I square a double of something, I'm squaring the 2, which ends up quadrupling the distance by a factor, or multiplying it by a factor of 4. All right, last page. Missy DeWater, the former platform diver of the Ringling Brothers Circus, dives from a 19.6 meter high platform into a shallow bucket of water. See the diagram at the right, this crudely drawn diagram. State Missy DeWater's acceleration as she is falling from the platform. So she is falling through the air. We're going to assume that acceleration is -9.8 meters per second squared. what assumptions must you make in order to state this value as the acceleration? So there's two things. She is not touching any object or surface, and we're ignoring air resistance. So those are our two assumptions we make with free fall, and so I can assume the acceleration is constant. So the velocity of Missy Dewater after the first half of the fall is represented by an arrow. The size or length of the arrow is representative of a magnitude, which just means the size of her velocity. The direction of the arrow is representative of the direction of her velocity. For the remaining three positions, construct an arrow of approximate length to represent the velocity vector. So, if this first arrow on this diagram on the right is that long, what's her velocity going to do as she falls? Well, her velocity is going to increase in the negative direction, so I should still put my arrows down, but they should progressively get longer and longer to represent that that speed is increasing, or that velocity is increasing downward. So for C, use kinematic equations to fill in the table below, and at the very bottom it says show your work for one of the rows of the table. So let's just talk about what would I use to figure out the velocity, the distance fallen, and the height. So velocity, I've got time. I know my initial velocity is 0. I can get my time values. I know my acceleration. So if I'm looking for, these would be all final velocities at those times. Then I'm going to use this first equation for this first column. If I want to know the distance fallen, think of this as dropping something. We just did this on the previous page. I'm going to use the second equation for this column. And remember, this middle term cancels because my initial velocity is 0. So the distance fallen will just be 1/2 acceleration times time squared. So velocity. If the velocity, let's just show the first one, and then we'll continue doing the other three. So the first one, my final velocity after 5 seconds, initial velocity was 0, acceleration is negative 9.8, and the time was 0.5 seconds. If I multiply those out, I get a velocity of negative 4.9 meters per second. If I use the same equation but put in 1 second, I get a negative 9.8 meters per second. If I use 1.5 seconds, I get a velocity of negative 14.7 meters per second. And if I do a full 2 seconds, I get a velocity of negative 19.6 meters per second. Again, I'm just changing the time in this equation and getting that velocity. So you see the velocity is increasing in the negative direction. For distance fallen, let's do the first half second. So acceleration is negative 9.8. Time would be 1/2. So 1/2 times 9.8 times half squared would be a distance fallen of 1.225 meters. If I change that to 1 second, then that would be 4.9 meters. If I change the time to 1.5 seconds, distance fallen of 11.025 meters. And then for 2 seconds, you're going to get a distance of 19.6 meters. So that's the distance fallen when I plug in the times into this equation, changing the time from 0.5 to 1 to 1.5 to 2. So that's the distance fallen. Now what's the height? Well, it starts out at a height of 19.6 meters. A half second later, it's fallen 1.225 meters. So it is now at 18.375 meters. I subtracted this from that height to get my new position. I'm going to do the same thing for the next one. If after a half second, well, I'm going to do the same thing for the other three. The distance fallen after 1 second was 4.9 meters. So how far is that, or what does that take away from 19.6? That brings me down to a height of 14.7. After 1.5 seconds, it has fallen 11.025 meters, which brings it down to a height of 8.575 meters. And then after 2 seconds, it has fallen 19.6 meters. It started 19.6 meters high, so after 2 seconds, it has reached the ground at a height of 0 meters. So this is just some good practice to keep using our equations over and over to fill in these values. Now, Michael Jordan was said to have a hang time of 3 seconds, at least according to a popular Nike commercial. Use kinematic equations to determine the height to which MJ could leap if he was wearing Nike shoes and had a hang time of 3 seconds. So before I even write out my variables for this problem, what does a hang time of 3 seconds actually mean? If Michael Jordan jumps, a hang time of 3 seconds is the entire time he was in the air. If I want to know to what height could he leap, I'm looking for the position at this point, which is exactly halfway through this motion. So I need to figure out, okay, what's the time it takes to get to the max height, not the entire hang time. So the time it takes to get to that max height for this problem is exactly half of the hang time. And that's only the case if your starting and ending heights are the same. So if you start on the ground, end on the ground, you can just divide that by 2. That gives you the time to the max height. So what the motion up to the max height and down from the max height are the same. They're just flipped. One's positive, one is negative. So if I'm only going to focus on this first section, let's write out our variables. All right, I'm looking for the displacement. I'm looking for that height to which he jumps. Don't really know how fast he jumps off the ground. But what I do know is that the max height, the velocity at the top of your path, is 0. There was a whole video on that from Flipping Physics, so we should know that by now. My acceleration, he's in the air in free fall, is a negative 9.8 meters per second squared, and the time is 1.5 seconds. So here's one of those problems where we have to actually use 2 steps. In none of our problems am I missing initial velocity. So I kind of have to know that to figure out this height. So first, let's figure out what that initial velocity was. How fast did he jump off the ground? The final velocity was 0. Acceleration is negative 9.8. 1.5 seconds. You get initial velocity 0 equals initial velocity minus 14.7 meters per second. So that must mean my initial velocity was 14.7 meters per second. So now that I know that, I can either use the second or the third or even the fourth equation to solve for this displacement. How high did he jump? I'm going to use the third just because. So final velocity was 0. Initial velocity was 14.7. Don't forget to square it. 2 times negative 9.8 times my displacement. All right, 14.7 squared
is 216.09. 2 times 9.8 is negative 19.6. So if we solve for our displacement here, we're going to end up dividing 216.09 by 19.6, and we get a displacement of 11.025 meters, which is extremely high and a gross exaggeration of Michael Jordan's physical capabilities. This probably was from Space Jam.